All right, I'm going to go over some of the last couple problems on the notes for derivatives of sine, cosine, tangent, cotangent, secant, and cosecant that I maybe didn't get to in class. So here is one of the ones that I wanted to work with you. And if I'm given a function f of x equals secant x over root x, there are two ways that I can actually compute this derivative. And I can use the quotient rule as it's written, or I can rewrite this as, first of all, I'd rewrite it anyway. So I could rewrite this as f of x equals secant x over x to the 1/2 and change the square root into its exponential form. Or you could take the derivative saying f of x is equal to secant x times x to the negative 1/2, where you move the power function from the denominator into the numerator with a negative exponent. And we could use the product rule on this one and the quotient rule on this one, and we'll get the same results. Okay, so I'm going to do the quotient rule first. So f prime of x is equal to the denominator, which is x to the 1/2, times the derivative of the numerator, which is secant x tan x, minus secant x, which is the numerator, times the derivative of the denominator, which is 1/2 x to the negative 1/2, all over the denominator squared. Well, the denominator squared here is x to the 1/2 raised to the second, which is just x. All right, now, in this problem, I'm going to rewrite it, and this will be x to the 1/2, secant x tan x minus secant x times 1 over 2 x to the 1/2 if I keep the the exponents positive. Okay, now I have a double-decker fraction here, and I like to eliminate those double-decker fractions, and there's an easy way to do it. If you were to take this fraction and to clear the fraction in the numerator, we could multiply it by a favorable factor of 1, and the favorable factor of 1 here would be 2x to the 1/2 over 2x to the 1/2. Now, why is that? Well, if I multiply this in, you'll see that the denominator here goes away, which is really nice. And then I have to add the exponents here. So here we go. So I'm going to distribute this. So 2x to the 1/2 times x to the 1/2 is going to be 2x to the, and I would add 1/2 and 1/2 and get 1, because when you multiply having the same base, you add the exponents. And so I get 1. So this is 2x secant x tan x minus just secant x, because this obviously cancels with the denominator here. So I've done my job and eliminated the denominator in the numerator, which is nice. But then I've added some to the denominator here. So this is going to be 2x, and this is x to the first. When I add the exponent here, it would be x to the 1/2 plus 1, which would be x to the 3/2. And we could simplify this maybe one more step by saying secant x out here times 2x tan x minus 1 all over, right? If I just factor the secant x out, 2x to the 3/2. And that would be the derivative, okay, using the quotient rule. It is messy, but it's pretty effective. Let's try it with the product rule. So I can say that f prime of x here is equal to, using the product rule, this would be first secant x times the derivative of the second, which would be negative 1/2 x to the negative 3/2, plus second, which would be x to the negative 1/2, times the derivative of the first, and I'm running out of space here, but that would be secant x tan x. So secant x tan x. Sorry about the small writing here. All right, and I'm going to factor out, I'm not going to factor anything out. I'm going to put things where they belong first. So f prime of x is equal to, well, both of these go in the denominator, so this is going to be negative secant x over 2x to the 3/2 plus secant x tan x over x to the 1/2. All right, and so that would be using the product rule. Now you have two fractions here, so if you set this equal to 0, you'd have to find a common denominator to solve for when it was 0 or when it was when it was equal to 0 when the denominator is equal to 0. But if I were to find, I'm going to prove to you that these are the same, they're equivalent. If I were to find a least common denominator here, it would be 2x to the 3/2. Now, why do I say that? Because x to the 3/2, mathematically, x to the 3/2 is really equal to x to the 1/2 times x to the 1/2 times x to the 1/2, isn't it? So this x to the 1/2 right here is actually a factor of this. It's like trying to find a common denominator between 4 and 2. Well, what would you use? You would certainly use 4 because that had the factor of 2 in it. Well, x to the 1/2 is a factor of x to the 3/2. So that's why this would be the least common denominator. And so I don't have to multiply anything by this one because it already has that denominator. And then I have to multiply this part by the part of the denominator it doesn't have. Well, it's got an x to the 1/2, so all it's missing is an x and a 2. So this would be plus 2x secant x tan x. And that would be f prime. And you'll see, if I were to factor out a secant x again, in the numerator, I get 2x tan x minus 1, which looks remarkably familiar. It is incredibly equal to the one that I have right here. Now, when we are doing applications of derivatives, what I like about the quotient rule is it already gives you a common denominator. It's already built in the calculation. Here, it takes a little bit more algebra for you to find a common denominator and have a fraction that you can set equal to 0 and undefined. So this is obviously two ways to find the derivative, one using the quotient rule and one using the product rule. All right, second problem I wanted to be able to do with you here is this next problem, which is like all the other derivative problems that we've done, but now we're going to involve trig equations in them. So this question says, find the equation of the tangent line to the curve y equals sine x cosine x at pi over 4. Okay, so my function is y equals sine x cosine x, and they want to find the tangent line at pi over 4. So there are two things you always need when you find an equation of the tangent line. You need to have a point and a slope. Well, here they only give me part of a point because they tell me that my x is pi over 4, but I don't have a y to go with it. So what do I have to do? Well, I have to say y of pi over 4, which means I plug my pi over 4 into my equation here, and that's going to be the sine of pi over 4 times the cosine of pi over 4. And I know this is a trig value that everybody's most familiar with. It's root 2 over 2, root 2 over 2. And if you simplify that, that's 2 over 4, which is equal to 1/2. So the other part of the point is 1/2. So we're going to put that right here. So I have half of what I need. Now I need the slope. Well, lucky for us, the derivative gives us a slope. So let's find the slope, the derivative. So I'm going to find the derivative and say dy dx here is equal to, well, this is a product, right? I have two functions that I'm multiplying together. And sine x is my first one and cosine x is my second one. And so to do this derivative, you say first, which is sine x, times the derivative of the second, which is the derivative of cosine, which is negative sine x, plus second, which is cosine x, times the derivative of the first, which is cosine x. And if I simplify that, I get negative sine squared x plus cosine squared x. And if I rewrite this in a different order, where I have the positive term first, this would be cosine squared x minus sine squared x. And I hope all of you are thinking to yourself, wow, I've seen this before, and it's not the big one because the big one is cosine squared x plus sine squared x. That equals 1. But what happens when it's subtraction here? It's another identity. And that identity is, that's right, I heard it, it's the cosine of 2x. It's the double angle for cosine. Okay, but that's not what we want. We want, this is a function for all the slopes. I only need the slope when x is pi over 4. So I'm going to say such that x equals pi over 4. And then we're going to find that this is equal to the cosine of 2 pi over 4, which is cosine of pi over 2, which is just 0. So the slope is 0, which means we have a horizontal tangent line. But if I'm going to write the equation for the tangent line at pi over 4, 1/2, I would say y minus 1/2 equals the slope, which is 0, x minus pi over 4. And for us, this 0 slope over on this side just wipes out this term, so we're going to end up with y equals 1/2. And there's our horizontal tangent line. And we can see that it works, because here we go, we'll graph it on Desmos. I have y equals sine of x times cosine of x. There's our beautiful function. And my point, we said, was, whoop, I gotta click over here. Whoop, I didn't mean to do that. I want it centered. Okay, so that's going to be pi divided by 4, comma, and we said our y value was 1/2. So there's our point, and sure looking like a horizontal tangent there. And if we say y equals 1 divided by 2, there it is. There's our tangent line at our specified point. Okay. So that's pretty awesome. All right. Last problem I wanted to do together really quickly is this question where it says find the higher derivative, which is the 2017th derivative with respect to x of 2 cosine x by finding the first 8 derivatives and observing the pattern that occurs. Well, since this is the year 2020, let's find the 2020th derivative. Okay, just for fun. All right, but they want us to find the first 8 derivatives. So I'm going to write down y equals 2 cosine x. Well, y prime, which would be the first derivative, is going to be 2 times the derivative of cosine, which is negative sine. So this will be negative 2 sine x. Y double prime is going to be the derivative of negative 2 sine x, which will be negative 2 times the derivative of sine, which is cosine x. Y triple prime is going to equal negative 2 times the cosine, the derivative of cosine, which is negative sine. So this will now be a positive 2 sine x. And the fourth derivative, and this is how you write that. You put a 4 up there with a set of parentheses, equals, all right, 2 times the derivative of sine, which would be 2 cosine x. And note, we've arrived back where we started, but they want the first 8 to see what the pattern is. So the fifth derivative is going to be the derivative of, or 2 times the derivative of cosine, which will be negative sine. So this is negative 2 sine x. The sixth derivative is going to equal negative 2 times the derivative of sine x, which is cosine x. So this will be negative 2 cosine x. The seventh derivative is equal to negative 2 times the derivative of cosine, which is negative sine. So that's going to be 2 sine x. And the eighth derivative is going to be the derivative of, or 2 times the derivative of sine x, which is 2 cosine x. And again, we've arrived at the beginning, once where we started, right? So what we should notice is that every, it looks like, fourth derivative, what happens? We end up with the same function for the derivative. Do you see that? So if I need the 2020th derivative, I need to figure out where I fall in this chain. Well, it looks like I need to divide it by 4. So what is 2020 divided by 4? Well, that's just 5, and that's 20, and then I carry down that, and that's 0, right? And then 2, and then a 0, and I bring down the 20 here. And it's 505 with no remainder. So if there's no remainder, that means I'm going to go through this pattern 505 times, and I'm going to end up on 2 cosine x. So the 2020th derivative of 2 cosine x is equal to 2 cosine x. Now, if they had asked us, and I was doing it 2020 because that's what year it is now, but in years past I've used the previous year, so 2017. So if this is the 2020th derivative, this would be the 2019, the 2018, and the 2017 derivative would be negative 2 sine x. Okay, so that's how you work it. I thought this was kind of a cool problem to see because these trig functions actually repeat themselves after a certain number of derivatives, and we can see that it's after every 4 you're going to get the same one. All right, so those were the last 3 problems I wanted to get to in class that I didn't get a chance to. So you guys have a great day, and we will talk to you another time. Thanks.